Okay, so there are the sum from n equals to 1 to infinity of n plus 1 divided by negative 4 to the power n plus 1 zeta of n plus 1. And the answer here seems pretty complicated. Like I was afraid at first even try because it was so long, right? But later on, when I just attempted to solve it and use some differential and integrals, yeah, there's just a few of them. Those very easy tools. This this like interestingly simplified to like to some infinite series. Like there were two infinite series like which were pretty well known. Yeah, and those infinite series had complex sums due to which the answer seems complex. But the solution it wasn't like too hard actually. And I was pretty surprised at how this actually tricked me. Okay, let's try to solve it. Now, first of all, of course, we will try to break zeta into the sum because without that, it would be pretty complex to do. So, sum from n equals to 1 to infinity, n plus 1 to the power divided by minus 4 to the power n plus 1. And now zeta can be broken into k equals to 1 to infinity of 1 by k to the power n plus 1, right? Of course, what I will do is I will intersect in the sums, right? Sum, first of all, these are constant which can be taken inside the sum and then intersect in the sum. Sum from k equals to 1 to infinity, sum from n equals to 1 to infinity, and then this will be n plus 1 divided by minus 4 to the power n plus 1 by 1 by k to the power n plus 1s. Okay. Now, what I was trying to do was I was trying to get rid of these numbers in the numerator. Of course, there are geometric series also with the ands in the numerator, but that if I could get rid of these numbers, then it would be easier. Yeah. So for that, what I thought was the I can get this like n as a derivative of this expression, right? K to the power n plus 1. So yeah, I should try to. I mean, this can be. I can get this because the power comes in front of right in front. So I was trying to use that, and then what I thought of doing was now I can write this as sum from k equals to 1 to infinity, sum from n equals to 1 to infinity. Now this is, let's say, n k to the power minus n minus 1, and then plus k to the power minus n minus 1 divided by minus 4 to the power n plus 1. Okay, now if I want this to be derivative, there should be minus 1 over here, right? Minus n will come if, let's say, if there was k to the power minus n, derivative will be minus n times k to the power minus n minus 1, right? So instead, what I can do is, since this power is also minus times n plus 1, what I can also here is n plus 1, so what I can do is basically remove the minus 1 to the power n plus 1 from here and add it to these terms. Yeah. In that way what happens is, okay, if I do it like this, now what happens is, if I have minus k to the power minus n, if I differentiate this with respect to k, first of all I get this and again I get a minus 1, right? So due to which this cancels and balances. Now I have this expression n to the power minus k and minus 1 minus n minus 1, which is exactly what we have over here. Now for this one also, just integrate this, we will get what needs to be differentiated. Yeah. So now I will write this as, this will be the derivative with respect to k, partial derivative with respect to k, sum from k equals to 1 to infinity, sum from n equals to 1 to infinity of, now I will integrate this 1 by 4 to the power n plus 1, and this is minus k to the power minus n plus, and then again its integral is just minus k to the power minus n by minus n times the also we will have minus 1 over here because k has minus thing, so its integral we also have minus 1 over here. Now this thing cancels out. Yeah, now it will be easier to solve it because there are no such n's to distract us. There is an n, but this can be solved as log, right? We know that x to the power n by n can be solved as log because this is just minus log of 1 minus x. We know that, right? If n is going from 1 to infinity and the modulus of x is less than 1. Yeah. Okay. Now over here we have partial derivative with respect to k. So I'm going from k equals to 1 to infinity. So I'm going from n equals to 1 to infinity. Now this is, I can take 1 by 4 out because I want to merge this 4 to the power n with k to the power n. Yeah. So that gives me minus 1 by 4k to the power n plus now this also is minus 1 by 4k to the power n divided by n, right? Now 1 by 4 partial derivative with respect to k, sum from k equals to 1 to infinity. Now if I sum this, we know that since k is going from 1 to infinity, the ratio is just minus 1 by 4 times the k, right? And we know that since k is in this range, for every positive k going from 1 to infinity, this ratio will be less than 1. Of course, yeah. That's clear because of course you can put the value of k and see that this is less than 1. I need not prove that. Okay, yeah. So this is also here of course the modulus of these things is less than 1. If I have to write this, modulus of 1 by 4k is less than 1 for k belongs to 1 to infinity. Yeah, 1 included. Okay, so that's why the sum will be a by 1 minus r. That means it will become plus. And over here it will be x to the power n by n is minus log of 1 minus x. So that is minus log of 1 minus 1 by 4k, which is plus 1 by 4k. Right? So we have 1 by 4 partial derivative with respect to k, sum from k equals to 1 to infinity, and now this is minus 1 by 4k plus 1, and over here we will have minus log of 4k plus 1 divided by 4k, right? Yeah. Now let's differentiate this expression with respect to k. So 1 by 4 sum from k equals to 1 to infinity, and this is 1 by 4k plus 1 square times 4, right, minus, and this is 1 by 4k plus 1 times 4 plus 1 by 4k. This plus because I have been like separating this log into two different logs with negative sign in between. Negative and negative is positive, times 4. Now you might notice that 1 by 4 cancels the 4's, right? So we have a really cool sum over here. Sum from k equals to 1 to infinity, 1 by 4k plus 1 squares plus sum from k equals to 1 to infinity, 1 by 4k minus 1 by 4k plus 1. Notice that I can like make this sum and the other sum in a different, I can write this in different sums, but I cannot like also separate these two because these two are not convergent sum. Their difference is convergent, but these alone are not convergent, so I have to write them into single ones, right? I mean into a common sum, and this is convergent, so I can like write it outside, I mean write it separately. So, and now till now there was nothing really difficult, right? And now why this abstract or different like vague answer? Because now these are well-known sums with well-known answers, yeah, and their answers are a bit complicated. Now let's see how to evaluate these two well-known sums. It's not really hard. We already know the answer for this one, but let me show you how do we find that. Now for the first sum is basically 1 by 5 square plus 1 by 9 square plus 1 by 13 square plus 1 by 15 square and so on, right? So what's basically happening here is that these differ by 4, except that we don't have 1 by 1 square over here. If we had that, it would look good, right? We don't have that. Now let's try to evaluate this sum over here. So for that we will use other well-known sums. I don't know how many of you have seen this sum. This is known as this sum is known to converge to a value which we don't know. I mean, which we know, but whose decimal approximation we know, but not the entire decimal expansion. And this sum is supposed to converge to a value which is known as Catalan's constant, and another is this sum, which is formed by just the odd numbers of the Riemann zeta of 2, right? And this is equal to, since the even terms of the Riemann zeta function are removed, this can be considered as Riemann zeta of 2 minus 1 by 2 square times Riemann zeta of 2. Yeah, because if I multiply Riemann zeta of 2 by 1 by 2 square, only even terms will be there, and subtracting even terms from Riemann zeta of 2, this gives us the odd terms, right? Now this is Riemann zeta of 2 times 1 minus 1 by 4, which is 3 by 4, times Riemann zeta of 2. Riemann zeta of 2 is pi square by 6. So 3 by 4 times pi square by 6, and this is pi square by 8, right? So this sum over here, this is pi square by 8. Now if we add these two sums, what we get is g plus pi square by 8 will be 2 times of our required sum, 1 by 1 square, 1 by 5 square, plus 1 by 9 square, and so on, right? This is 2 times our required sum, right? If we add these two, because odd term will cancel, even terms, there will be 2 even terms, right? Now I can take this 2 to division, so g by 2 plus pi square by 16 is equal to this sum, but notice that we also don't need the 1 square, so I can subtract that too. First divide by 2 and then subtract the 1. So this is our required sum, 1 by 5 square plus 1 by 9 square plus 1 by 13 square plus 1 by 17 square, and so on, right? Yeah. So we have the value of the first person, which is g by 2 plus pi square by 16 minus 1. Okay, that looks good. Now next one is this sum. This sum is also well known. I mean, this is pretty standard sum. Sum from k equals to 1 to infinity. I can take 1 by 4 common, right, from both the sums. So I have 1 by k minus 1 by k plus 1 by 4. Now if you know a bit about digamma function, we know that digamma of g plus 1 is equals to negative Euler-Masoni constant plus sum from k equals to 1 to infinity 1 by k minus 1 by k plus g, right? Using this definition of digamma function, we know that this sum is just equal to, so since there is g as 1 by 4, there will be digamma of 5 by 4, digamma of 5 by 4, and plus the Euler-Mastroianni constant, right? Yeah. Now we need to find diagram of 5 by 4 now, so that we will have our answer. This is a constant, this is a function, because this is diagram function of 5 by 4. We need to find the value of that function at 5 by 4. This is a constant which is 0. This is around 0.577, something like that. Okay, now let's see how to find a diagram of 5 by 4. To find diagram of 5 by 4, we need to use a bunch of properties of diagram function. There is a digamma addition formula which we will use to find this value. Digamma addition formula. It's not too hard actually. I mean, we will not go to the proof, but we will just use the formula. We know that sum from this formula, we know digamma sum from k equals to 1 to n minus 1 of digamma k by n. This will be equals to minus of n minus 1 Euler-Mastroianni constant minus n ln of n. This is the formula, and from this formula we'll try to find digamma 1 by 4. So for that we need to put n as 4, right? So if we put n as 4, putting n as 4, what we get is digamma of 1 by 4 plus digamma of 2 by 4 plus this will go up to 3, right? So digamma of 3 by 4 will be equals to minus 3 times Euler-Mastroianni constant minus 4 ln 4, right? Yeah. Again, now we don't know these two terms, but we know that digamma of 3 by 4 is related to digamma of 1 by 4. So that's how we can find it. Yeah. And now let us see how digamma 3 by 4 and 1 by 4 are related, and also we can find digamma 1 by 2. So yeah, we will find them. Okay, now how are these two related? These are related from the reflection formula. These two are related from the reflection formula. Let us see that. We know that in the gamma function, the reflection formula is gamma n, gamma 1 minus n is equals to pi by sine n pi, right? Now over here what you can do is you can take the log of the items and then differentiate it, because we know that digamma is just the derivative of log of gamma. If you take log gamma and then differentiate this will be digamma, right? So you can use that and get the formula that digamma of 1 minus n minus digamma of n. Yeah, sorry, I don't think this is the. Wait, let me differentiate. I forgot the order. Let me do it. So log of gamma of n plus log of gamma of 1 minus n is equals to minus pi cosec n pi, right? What am I doing? I'm sorry. Minus pi log sine n pi, right? Minus pi log sine n pi. Now this is just digamma. If we differentiate digamma of n, if we differentiate minus digamma of 1 minus n is equals to, if we differentiate minus pi, this is 1 by sine n pi times cos n pi times pi, right? Pi is there. Now this is okay, yeah. So eventually this minus sign causes this to change the order. Digamma of 1 minus n minus digamma of n is equals to this. There will be. I'm sorry. This is log pi. Also there is plus log pi, which eventually goes to 0, but I wrote it in the wrong way. Plus 0, yeah, good, fine, now fine. And this pi is not here. So okay, minus pi cot n pi. Now it's good. But again, I took cot pi minus to other side, so there's no minus again. This is hella confusing. Yeah. Is it right now? Yeah, it's right now. Okay, fine. I'm sorry. Okay, so yeah. So this is the formula, right? Now, can I find diagram 1 by 2 from this formula? I wonder if I can. 1 by 2 cot pi by 2 is 0. Oh, I cannot find because both are just diagonal 1 by 2, 1 by 2, which cancel out, so I get 0. No, I cannot. But still, even though I can find diagonal 1 by 2 from this one, I can still find the relation between these two, right? So if I so from here what I get is diagamma 1 diagamma of my 1 minus n minus pi cot n pi is equals to diagamma of n. That gives me diagamma of n is minus pi cot n pi plus diagamma of 1 minus n. Yeah, using this, diagamma of 3 by 4 will just be something plus diagamma of 1 by 4, and that changes it to the form of 1 by 4, right? Now let's see how to find diagamma of 1 by 2. So for that, to find diagamma of 1 by 2 now, we can again use the same sum. In the sum we had that sum from k equals to 1 to n minus 1 of diagamma k by n is equals to minus of n minus 1 Euler-Masonic constant minus n ln of n, right? If you put n as 2, this sum goes from 1 to 1. So diagamma of 1 by 2 is equals to minus of 2 minus 1 is just 1 minus gamma minus 2 ln 2. So we got this value, right? So now I think we are closer to solution. We can also find this diagonal 1 by 2 from the duplication formula as well. Okay, now diagamma of 1 by 4 minus gamma minus 2 ln 2. Now this is minus pi cot 3 by 4 pi plus diagamma of 1 by 4. Yeah, which is minus 3 gamma. So minus 3 Euler-Masonic constant minus 4 ln 4, right? Now 4 ln 4 I can write this as 8 ln 2 because other is 1 is 8 ln 2. Okay, now there are two diagamma 1 by 4s, right? And then we have this equals to minus 2 Euler-Masonic constant minus 6 ln 2, and this is minus 1, so plus pi and then minus pi. That means diagamma of 1 by 4 is just minus Euler-Masonic constant minus 3 ln 2 minus pi by 2. Yeah, now this is our second value, second sum value. Now let's substitute it over here. So 1 by 4 diagamma 5 by 4. Okay, now again it's diagamma 1 by 4, right? Now for diagamma 5 by 4, we know that diagamma 1 plus n is diagamma of n plus 1 by n. I'm giving a bunch of stuffs and it might be feeling like complicated, but no, this is it. This is maths. Okay, now if you put 1 by 4 over here, diagamma 5 by 4 is diagamma 1 by 4 plus reciprocal of 1 by 4, which is 4, right? Now if you substitute this, what we will get is diagamma of 1 by 4 is minus gamma minus 3 ln 2 minus pi by 2, and again plus 4 as well because yeah, and plus Euler-Masonic constant. This cancels out and I get minus 3 by 4 ln 2 minus pi by 8 plus 1, right? Okay, yeah. Now finally we did this sum as well. This one actually looks pretty simple, but this has very complicated sum, right? Yeah. What to do? Now this is minus 3 by 4 ln 2 minus pi by 8 plus 1. Yeah. 1 cancels out and then we get the sum g by 2 plus pi square by 6 minus pi by 8 minus 3 by 4 ln 2, which is the required sum. And hence we answered the question. We found the value g by 2 plus pi square by 6 minus pi by 8 minus 3 by 4. Yes, that's the answer. So we can see that how diagamma addition formula was helpful for us to find both diagamma 1 by 2 and diagamma 1 by 4, right? And also we found how helpful it was the reflection formula of diagamma function. I think it's better to remember this formula because yeah, just like how I forgot there's chances that you might also forget it, right? Yeah, so try to remember that. Else, mm, other than this, what else did we use? We used the sums, the sum of cat Planck's constant and zeta function, and also differentiation also made it easier to solve, although it could have been solved without differentiation too. Yeah, so that it is. And yeah, with this nice sum we learned a lot of properties. I hope that was helpful for you. Thanks for watching, and look forward to seeing you in the upcoming videos too. Also, like previous to this video, I have uploaded a video where I solve Gaussian integral using simulation. Hope you enjoy that and the use of Monte Carlo simulation. Yeah, that is it. Thank you.